In this video, we will explore the relationship between a right triangle and its incircle and discuss that relationship in terms of a theorem, and then we will prove that theorem. So we start with a right triangle and we mark its acute angles as alpha and beta. In other words, alpha and beta are complementary angles, so if you add them together you get 90. And then inside of that triangle we will inscribe a circle. In other words, a circle large enough to touch each of the legs of the triangle at a tangent point. We'll mark the radius of that circle as r, and we'll make two assertions. Assertion number one is that the area of a right triangle can be determined using only its incircle and one of its acute angles. And assertion two is that the area of a right triangle is in fact equal to r squared times secant theta plus tangent theta times cotangent theta plus cosecant theta, where r is the radius of the incircle and theta is either of the two acute angles. So to state those assertions in the form of a theorem, we have Ingalls' theorem of right triangle area via incircle, which is that the area of a right triangle can be calculated by dividing the hypotenuse at its incircle tangent point and then multiplying those two resultant lengths together. Further, the corollary is that the required two segments of the hypotenuse can be calculated as r squared times secant theta plus tangent theta and r squared times cotangent theta plus cosecant theta. Therefore, the area is as previously stated. In order to prove this theory, we'll create a structure around the triangle. Specifically, that structure will be a rectangle split into 3 rows and 3 columns. We'll start by creating 2 lines, one vertical and one horizontal, where each of those lines passes through the center of our incircle. Then we'll create a horizontal line at the intersection point of the hypotenuse and the vertical center line of the circle, and then a vertical line that likewise includes the point where the horizontal line that goes to the center of the circle crosses the hypotenuse. So this will give us 3 rows and 3 columns. And the important thing about this structure is it will create a number of triangles, and the important aspect of each of these triangles is that they are in fact similar to the original triangle itself. In other words, the acute angles of each of these right triangles is the same as the acute angles of the larger triangle that we're trying to find the area for. So here you see the area that we're looking to find. We can find either the area of the bottom triangle or the top triangle, as these areas will be the same and in fact be exactly equal to half of the area of the rectangle. So for the moment we'll put that structure aside and we will label our rectangle's base B and our rectangle's height H. Then we'll mark the tangent point on our base and on our height as the radius of the incircle. Given this, we can subtract the radius from the base, producing a chord B minus R, and do the same thing with the height, producing a chord H minus R. From here we can use the two-tangent theorem, which says that if any two segments are tangent to a circle and that they start at the same point, those two segments are the same length. So this allows us to see that the hypotenuse is in fact equal to H minus R plus B minus R. Now, if we were to multiply H minus R times B minus R, we would get the expression HB minus HR minus BR plus R squared. And if we apply those terms to the structure that we created a moment ago, we can see that HB equals the entire area of the rectangle, and from that we subtract HR, which would be the leftmost column of our structure, and then subtract BR, which would be the bottom row of our structure, and we note that because we've subtracted R squared twice, as it was included in each of the rows and the columns removed, we have to add one of those back in. That leaves us with a smaller rectangle, and now the question is that smaller rectangle equal to the area of the large triangle? And as we look at the area that we do have covered and compare it with either of the triangles in the rectangle, we see that we have neglected 2 rectangles, and you see those here marked in yellow, and we have added a superfluous triangle in the light blue. So in other words, the rectangle that we have covered leaves a couple of triangles out, but includes a triangle that was outside of the area of the larger triangle we were trying to determine the area for. So the question then becomes, is the area left out equal to the extra area that we've included? or more specifically, is the area of the two yellow triangles left out equal to the area of the blue triangle included? And so in order to calculate that area, we will look at each of these rectangles in turn and determine its dimensions. So we start with the one at the top, and we can see that one of its legs is equal to r, and one of its angles is equal to beta. So let's take a closer look at that. If that adjacent leg is equal to r, we know that the hypotenuse must be r divided by cosine beta, otherwise known as r times secant beta. And if the hypotenuse is r secant beta, we know that the side opposite must be r secant beta times sine, which is otherwise written as r tangent beta. So that's the first triangle that was left out of the area. Now let's take a look at the superfluous triangle. And here we can use angle alpha and see that this length is r tangent of alpha, and that length is r cotangent of alpha. The base is r secant of alpha, and the height is r cosecant of alpha. Now we could use the angle alpha to determine the lengths of each of these legs. However, it will actually be a little easier to work with and remember our formula if we choose to use beta instead. Now, because beta is a complementary angle to alpha, what that means is trigonometrically we'll be using the reverse of all of these functions. So instead of using alpha, we use beta, and then the lengths of each of these legs of our triangle are as you see here. So having determined the dimensions of the erroneously included triangle, let's now take a look at the second neglected triangle at the bottom. And once again, we see that it has a leg equal to r, and this angle must be alpha because it is next to an angle beta, and the angle opposite that must be beta. And if that leg opposite angle beta is r, then we know that the hypotenuse must be r divided by sine, which is otherwise known as r times cosecant beta. And if the hypotenuse is r cosecant beta, we know that the adjacent side must be r times cosecant beta times cosine beta, and that's otherwise known as r times cotangent beta. So now we have each of our triangles mapped out, and what we want to do is plug those into the formula for a triangle to determine whether or not the two yellow triangles' area added together is equal to the blue triangle. So here are each of the legs of the triangles as we have determined them. Now let's remove everything that we don't need to determine the area of a triangle and take those lengths and plug them in to the formula for the area of a triangle. So the question is that a true statement? So to determine that, the easiest thing to do is to multiply everything by 2 to get rid of the half, and then divide everything by r squared to get rid of the r, and we end up with this equation where we simply have tangent beta plus cotangent beta is equal to secant beta times cosecant beta. And to see if that's equivalent, because these are all trigonometric functions with respect to the same angle beta, we can simply present these as the trigonometric ratios. So tangent turns into opposite over adjacent, cotangent turns into adjacent over opposite, secant turns into hypotenuse over adjacent, and cosecant turns into hypotenuse over opposite. Our next step is to combine the two fractions on the left and multiply the two fractions on the right, and this gets us opposite squared plus adjacent squared over adjacent times opposite being equal to hypotenuse squared over adjacent times opposite. Now at this point our denominators are equal, so we can just remove them from the equation, and we are left with a restatement of the Pythagorean theorem, which is obviously true. So at this point we have determined that h minus r times b minus r results in a series of terms that are in fact equal to the area of the triangle. And we can apply that either by splitting the hypotenuse up into h minus r and b minus r and multiplying them together to determine the area of the triangle, or we can calculate h minus r as r secant beta plus r tangent beta, and we can calculate b minus r as r cotangent beta plus r cosecant beta. So now it's a matter of taking those lengths and plugging them into the formula given, and we can see that h minus r times b minus r is in fact equal to r squared times secant beta plus tangent beta times cotangent beta plus cosecant beta. And that's the proof, QED. And thanks for watching.